Thank you for the introduction. Good afternoon, everyone. My name is Naama, and I'm here to talk to you about noise analysis in photosynthesis and how it can give us a fresh new perspective on the energetic dynamics occurring in the wonderfully complex process of photosynthesis. But first, what is noise? Perhaps, like me, you're thinking of something like this. But I'm not talking about acoustic noise. What I am talking about is signal fluctuations. When you subtract the average from a signal, for instance, voltage, you get the noise, the deviation from that average. And you can do a number of things with this. We focus on two. The first is a histogram to look at the noise amplitude distribution of the, and we can do a Fourier transform to look at the frequency spectrum distribution using a PSD, or power spectral density graph. But why is this even interesting? Usually, when we do experiments, we only look at the average of the signal. But we're missing a whole layer of information encoded in that noise. Now, this is not a commonly used tool in biology, but we've already shown this technique to be successful in a number of different organisms. The ones I want to talk to you about today are corals. In the coral monitoring system in Eilat, created and managed by Professor Moaz Fine, we monitor 3 different locations with 8 coral colonies each for a period of 4 years and ongoing, creating a huge database about an ecological keystone species at critical risk from climate change. Now, our measurement setup is as follows. We have a pulse amplitude modulated, or PAM, fluorometer, which sends pulsed excitation light and collects and measures pulsed chlorophyll fluorescence, originating from photosynthetic organisms residing within the tissues of the corals in a symbiotic relationship. Now, because these corals are measured in situ, in their natural environment, they're subject to a wide variety of conditions: different sunlight, temperature, and nutrient availability. And we can see how these factors influence the photosynthetic performance of the corals. The first and most striking finding that we saw is that noise is actually higher at night. If you look at the full width half maximum here, oh, it's not working, of the noise histogram, you can see that both for the shallow and the mesophotic, or the deeper colonies, the noise is higher at night. Each point on this graph represents a single colony at a single date period throughout the year, meaning that for different species, different seasons, and different depths, consistently we get a higher noise amplitude at night. Now, this really surprised us. How can it be that the noise is higher at night? We expected that during the day we'd have more photosynthetic activity and therefore more noise, but we got the exact opposite. To understand this better, we turned to our collaborators, Professor Corinne Dahmen and her students in Illinois, who study something called avalanche-type noise. It's most easily visualized as a positive feedback effect, a grain of sand toppling others down a mound. When they looked at our data, they saw multiple occurrences of avalanche dynamics during the night, but not during the day. So what's happening here? Well, we know that the main difference in the noise amplitude is concentrated in the lower frequency spectrum. Now, these are chemical reaction timescales, not physical ones. Couple this with the avalanche dynamics that we saw, we think there is a positive feedback effect of photosynthetic membrane reorganization triggered by the minimal light, which we attribute to the measuring light of our PAM, which means that corals may be sensitive to even very low levels of light pollution. Now, before I reach my conclusions, I'd like to thank my wonderful friends and colleagues at the Q&E and Karen Lab, and of course, thank you for listening, and leave you with the take-home message that fluorescence noise reveals novel and surprising energetic dynamics in corals, with implications for the role of light pollution in coral survival.
Thank you, Naama. Oh, looks like we have one question. Yes, go ahead.
Hi, thank you for the. Am I being too loud again? Sorry. Uh, for the interesting talk, I was wondering, does the noise also correlate to functional relevance in these systems? So, for instance, do you see uh, a different catalog of functions happening at night versus the day, and does the noise contribute to that?
So that's what's called an excellent question because I have a slide prepared. If you take a look here at the weighted Y2, so that's a standard measure of photosynthetic performance. We expect it to be higher at night because it's a measure of the quantum yield, the ability of corals to produce photosynthesis. And during the day, there are many reactions that you lose to heat stress. You have to manage the different energy levels. And as you can see, the two correlate. However, we get a better difference between the day and the night with our noise measures compared to the Y2.
Okay, nice. Thank you.
Naama, thank you for your beautiful talk. I wonder when you were collecting this data, how did you exclude the external environment factor, such as the ship that might nearby to their engine have no noise to affect the coral layer?
So let me just make sure I understood the question. You're asking how I remove background effects of the measuring system?
Yeah, how to exclude the other factor that actually might have effect on your experiment results.
Okay, great. So because these corals are measured in situ, in their natural environment, we can't. They're measured in a coral preserve, obviously. And the measurement system is such that it's specific sensors that just sit there. So aside from the measuring light, the sensors are not doing anything. Ships are not allowed to pass so close to the corals. But all the other natural factors, heat waves, different sunlight, cloud cover, they're all things that we incorporate into our study.
Thanks.